welcome to Lemop TV. Today we are discussing the principles of electromagnetic induction. Also, we'll discuss the history of the electromagnetic induction and the definition. We'll discuss Faraday's law and then we'll discuss Lenz's law. All this we're going to treat in the course of this video. Beginning from scratch, the history of electromagnetic induction is dated back to a scientist by the name Michael Faraday. He was one of the best scientists in physics that you could ever know of, and in chemistry as well. He developed the electromagnetic induction and their principles in 1820. So that is the history of the electromagnetic induction. Now, he was doing an experiment actually with a magnet, the north and south pole, and with a solenoid, a coil of wire with a solenoid, and then a galvanometer to indicate and detect the presence of current. So he was doing it with three objects: the galvanometer to detect current, the solenoid for movement of current and to indicate direction of the induced current, and then the magnetic field. All of this revolves around a particular principle, which is what we're going to discuss under the definition of the electromagnetic induction. Now, the electromagnetic induction, its definition states that it is defined as the process whereby an EMF is also known as voltage or current, is induced in a circuit when there is relative motion or relative movement between the coil and the magnet. And I stated earlier that the materials in the process are the magnet, the solenoid, and the galvanometer. These three things, mainly these two things are connected together. Then this magnet is moved towards and away from the solenoid. We notice therefore that a current is induced in that circuit, yes, and then the galvanometer will indicate directions of the current movement, of the direction of the current. All these things are what we're going to discuss here. Now, why does the current rather come up? How does the solenoid detect it? How does the magnet cause a current to be induced? It is related to one of the former laws which is still existing, which is still in use in physics, of the magnetic effect of the electric current, which I discussed earlier with you. This is saying that when current is passed in a straight wire, that you observe magnetic fields in concentric lines around it. Magnetic field in concentric lines around it. These are the concentric lines, magnetic field in concentric lines when it is moving. And I showed you how you can use it. The right hand rule, I gave you examples. I gave you the Maxwell corkscrew rule as well. To get more information about that, you can go to the initial video. Now, this is saying that when current is passed through a straight wire, you observe some movement in magnetic field. You don't see it, but you notice it by the movement arrangement of the ion filings that are on that part. Now, the same thing occurs in a solenoid too. When the current, there's no current pass now, but when the magnet is brought towards it, the solenoid, as the magnet is entering, the galvanometer indicates the current in the direction facing the direction of the magnet. The current is moving in the direction of that magnet, Then when it is moving away, something like this, when the magnet is moving away, note fully that you cannot identify the north and south pole of a magnet. This is just for clearance sake. Note fully that also when it is like this, the solenoid and then the magnet is moving away, notice that the galvanometer points the other direction away. Now this is related to the Lenz's law. Before we go there, I want to explain the Faraday's law because it's an important law in this process. Now, the Faraday's law states that a change occurs, or when a change occurs in magnetic flux linked to the circuit, it produces, or rather induces is the right word actually, it induces an EMF. It induces an EMF, note that, the strength of which is proportional to the rate of change of flux. That is, when there's a change in the magnetic flux that is linked to the circuit. That is, for example, now you have your solenoid connected to the galvanometer. Already some magnetic flux is existing here, some magnetic field is existing here. This now can act like a magnet because this galvanometer is used for detecting current, so this place already has some sense of magnetic flux. And so when this magnet comes in contact with, when it comes to contact with the, or comes closer, not in contact directly, not directly rather, when it comes closer to the solenoid, it induces a current, it is an EMF, and that EMF, the strength of the EMF, that is the weight of the EMF, is proportional to the change or the rate of change of the flux, which means the change occurs with time. And now you represent the EMF with E, and so it becomes, he said it is proportional, the EMF is proportional to the rate of change. We represent the, let's use the flux for the sign, the magnetic, M for magnetic flux, the magnetic flux, and then all over dt. This is the derivative for rate of change of the magnetic flux with respect to time. So E is directly proportional to this formula, and so E, because we need to make it equal, E is equal to N d O, not O rather, magnetic flux over dt. But there's something else we did not include. We need to have included a minus. Now, why is this minus there? This is what we're going to know under the Lenz's law. We are finally in the Lenz law, and it states that the induced EMF or the induced current always flows in a direction so as to oppose the change of flux producing it. Now this is very true because E is equal to minus N d, then the magnetic flux dt. Now there's something I did not explain initially. I didn't explain what this N meant. I didn't explain what this magnetic flux rather meant. So I want to explain them now. The magnetic flux actually represents the magnetic field in B, the magnetic field represented by B, the magnetic field of that magnet and around that solenoid or around that wire, and then the area of the coil, then cos theta, where theta is the angle between the magnetic field angle between the magnetic field and the plane of the area of the coil, the magnetic field and the plane of the area of the coil or of that wire. Now suppose we have our coil to be, okay, let's use a rectangular coil for example. This is a rectangular coil of wire wound in this form, having several turns. I will also explain for the solenoid as well. So this is a solenoid, also rectangular. Now this is the plane of this is the plane of this form right here. This is the plane of the coil. Then the angle between the magnetic field, okay, supposing you're bringing a magnet into like this, like assume this is your north pole and then this is your south pole. Assuming you're bringing a magnet into like this, the magnetic field is entering this direction. So the angle between the magnetic field, this is the magnetic field direction now, this is where it's going. Then the plane of the coil, this is the plane, that is the horizontal form, the horizontal plane of the coil. If the angle here now from here to here is our theta, so it is the angle between the magnetic field. A magnetic field is always experienced, the magnetic force is always experienced around the magnet. So the magnetic field interfering with the area, with the plane of the area of the coil, will produce an angle, and that angle, the cos of it multiplied by the area of the coil and multiplied by the magnetic field in Tesla, will give you our magnetic field in Weber. So what is it trying to say? Also the N is representing the number of turns. I didn't explain that in the initial number of turns of the wire, the number of turns of wire. Also for the solenoid it looks like this. Now how many turns of wire does this one have? This is the first turn, this is the second turn, this is the third turn, the fourth one, the fifth and the sixth. So the number of turns of wire is 6. So that is also important in determining the weight of the induced EMF E, that is in determining the amount of current that will be flowing. So the number of turns of wire is also important, because if the number of turns are high, then the current would also be high, but if it's low, the current would as well be low. Now he said the induced EMF also flows in a direction so as to oppose the change, which means that if the magnet is coming like this, the north and then the south, into the solenoid like this, it's coming in this direction. Normally the current is supposed to flow from the indication of the galvanometer. The current is supposed to flow like this, but what it does is that the current that is induced, the current that flows, will come in this direction, will flow in this direction, will flow so that it opposes this change. As this thing is coming, it is interrupting the magnetic field in the solenoid as well as in itself. So what it does is it creates an energy. The magnet moving creates an energy, and so that energy is opposed by the energy of the induced current, so that the energy put into the energy input will be equal to the energy output. So what it does is to make sure that there is no loss of energy, and so the energy that is inputted is also the energy that that is put in will also be the energy that will be put out, so that there is no loss in energy. So the induced EMF flows so as to oppose the change of flux, producing it. I hope you enjoyed every bit of this video. This was talking about the principles of electromagnetic induction, and I explained you the history and the definition, Faraday's law and Lenz's law. Now, the next video which we'll be treating will be on the differences and likely similarities, the differences and similarities between the Fleming's right hand rule and the Fleming's left hand rule. The similarities and differences where they both apply, we'll be discussing on it in the next video. Please endeavor to subscribe to this channel for more interesting videos. Thanks for watching. I hope to see you next time.